This is where we were talking about the operating system concepts, and I talked a little bit about the disks. We said that first we talked about this, right? Memory. When we said memory, we said we like our memory to be fast, large, and cheap, and we cannot have them that way all the time. If it is fast, it is not large. If it is large, it is not fast. If it is cheap, it is not fast. So usually this is faster if you go that way. This is faster if you go that way. This is fast. This is slow and large. Okay, no. This is slow. This is expensive. This is cheap. Small, large. Okay? So I cannot have fast, cheap, large at the same time. So I need to use all of these technologies at the same time if I want to do something useful. So we talked about registers and the core memory and then we were talking about the disks. And I am sure you looked at the structure of the disk before in some other classes in CSE 101 or something. In disk we have platters. You have many platters, sometimes tens of platters like these. And each platter, okay, each disk has a surface. The two sides of the disk, surface 1 and surface 0, two sides of this disk. I can write and read from those two sides, and I have a mechanical arms to read the data from the disk, to read and write data from the disk to keep my information. As I showed you last time, we said that there are tracks like that, and we have information in these tracks, ones and zeros. So I have this information, concentric rings like that, and there are thousands of them on this surface. And these heads, read-write heads, they move in and out. And while this spins at a very fast rate, like 10,000 RPM, 10,000 rotations per minute, I can read my data or write my data. And this was the idea in the 1960s and 1950s. The idea did not change, okay? The disks are working exactly the same way, only the rotations are now much more than it used to be. And the density of these data is much higher than what it used to be. As I said before, the size of these disks used to be like 60 centimeters, like this big, okay? This big disk. And you have only 3 or 4 disks in the same drive, and you can hold at most 1 megabyte of data, maybe at most in the 1960s, 1 megabyte of data. Nowadays, our disk sizes are very small, a few centimeters at most. I can have tens of them, tens of these disks in the same hard drive. My densities are very high, and I can store terabytes of data in a single small device. So only the capacities and the speeds have changed. The technology stayed the same. The main idea stayed the same. The other thing is that other than the mechanical disk, nowadays we have solid state drives. Okay, these devices are not mechanical, as I said before. Since they are not mechanical, they are a little bit faster, and they are not prone to mechanical failures, but they have their own problems. What is the problem with the SSDs? If you read and write too much, then they start showing some. Sometimes they can develop bad sectors. You cannot read and write to the same place of the SSD many times. They have some problem with this issue. With the mechanical disk, you don't have that kind of issue. There are some other issues with the mechanical disk, like the mechanical head. It has to move in and out, which is slow. We will talk about these later. Okay. So, remember this picture? This picture, general hardware. We said that each hardware has its own controller, an electronic device. Let's talk a little bit more about that. Okay, I/O devices. Each I/O device has a controller. It's an electronic device. That device is kind of an interface between the computer and the electronic device. The devices are very complicated, as I said before, and controller makes handling of this complexity easier for the computer, not for us, not for the computer programmer, but for the computer. And it does this by using this special software called device driver. Device driver is a middle layer software for the controller by the manufacturer. The manufacturer produces the hardware, for example, let's say printer, and printer has an interface. For that interface, it gives you this device controller, which is an electronic device, and then it provides a device driver. The device driver, we communicate with the device driver. The operating system communicates with the device driver to control the I/O device. That's the solution to make the handling of this complicated device easier for the operating system. So device driver becomes a part of the operating system actually. It becomes a part of the operating system because most of the time it runs in the kernel mode. If there is a problem with the device driver, it might crash the whole operating system, which is very dangerous. That's why you should write your device driver very carefully, or as an operating system designer, you should be very careful about installing new device drivers. If there is a problem with some device driver from some other company, then your operating system crashes, which is a bad thing for the operating systems designer. Okay. So let's talk about a little bit more I/O devices and how do you do I/O. Okay, when the CPU needs to load some data from an I/O device, what does it do and that kind of stuff. There are three methods. The first one is busy waiting. You all know this, right? You know this from the architecture class. You know these three. You know this, right? Biliyorsunuz değil mi? So the busy waiting is CPU waits until the I/O is over. What do I mean? CPU asks the I/O device to give some data, and it waits until the data is ready. What is the problem with this one? The problem with the busy waiting? Şu arkadaki bilgisayarı kapatsan, bilgisayarla oynama gözümün önünde ya. What is the problem with busy waiting?
CPU stands idle and it could process some other programs.
While the CPU can process some other program, yes, CPU stands idle because it is waiting for the I/O. So it is wasting the CPU time, which is not a good thing. That's why busy waiting, although it is very easy to implement, it has some efficiency problems. So to solve these problems, they came up with two solutions. One is the interrupts. CPU asks the driver to get the data, and it blocks the process that needs the data, and CPU immediately starts processing some other job. Okay, so CPU never stays idle. It just asks the device driver to get some data, and it immediately starts doing something else. When the data is ready, an interrupt is generated from the interrupt controller, and the process can start again because the data it is asking for is ready. So that's an interrupt. So the data transfer is done by the CPU again. You transfer the data from the device to the memory by the CPU. It is done by the CPU, but CPU CPU doesn't have to wait for the device to be ready to transfer the data. It can do some other job, which makes it more efficient than the busy waiting. Another more complicated or more enhanced way of doing I/O is the direct memory access, DMA. Okay, in the DMA case, CPU sets up the DMA chip. There's a DMA chip, okay, on the bus as part of the system. It says that I am going to transfer this much of data from this I/O device to this memory location, and DMA chip is responsible for doing that transfer for the CPU, and that's it. And the CPU can continue doing some other stuff. In this case, all the transfer is done by the DMA chip, not by the CPU, but the DMA chip. Input-output. But DMA chip is another chip. It's like a processor. Sometimes DMA chips, they have their own CPUs in them. So this is much more complicated than this one, and certainly from this one. Okay. But sometimes people prefer, even though they have the interrupts and the direct memory access, sometimes people prefer this one instead of these two. Can you guess what kind of situations I may prefer this one? See, busy waiting. Even though it is possible to use interrupts or the direct memory access, for some critical cases, busy waiting, they prefer busy waiting. Which one do you think is faster? Busy waiting interrupts or the direct memory access? Faster in terms of transferring the data.
Direct memory.
Direct memory access, why? DMA is a chip. Usually it has its own program. It's like a computer. So its job is, remember that 1405 computer, whose job is to use the punch card reader or the printer as a printer driver. Remember that computer? That computer is a computer, but it is not faster than the main computer, right? But it's still a computer. So its job was to make the main computer available to the important computation, right? So we still using it. We are still using it to make the life of the main computer a little bit easier or more efficient. But if we don't have such a constraint, if I have the CPU for myself, there is nobody else. CPU is much faster than the DMA chip, right? So if the CPU has time, if CPU doesn't have anything to do, then if the CPU transfers the data from IO device to the memory, it would be much faster than DMA doing it, or it will be faster than the interrupts. So sometimes, maybe for the embedded systems, instead of using direct memory access, I can use the CPU, busy waiting, to do the transfer myself, which might be more, which might be faster, much faster than doing it otherwise. Okay. So that doesn't mean that, I mean, the DMA transfer is more sophisticated. It doesn't mean that I should not do this. I should not abandon doing this altogether. No, sometimes I might need doing this busy waiting. Okay. So these are some methods that we use for I/O transfers, and we will talk about this when we come back to the I/O in one of the book chapters. This is a picture from the book that talks about the interrupts, the second one. Okay, so this is how the interrupt sequence works. CPU asks the disk controller through the driver, okay, to transfer some data, and CPU starts doing some other thing. It blocks the process and it starts doing some other thing. The disk controller gets the job, okay. It transfers the data. It says that the data is ready, and it asks the interrupt controller. To inform the CPU, about the interrupt. If the CPU is available, CPU stops doing whatever it is doing, then it can start transferring the data from the this drive or some other I/O device. So this is how many steps? There are 4 steps, right? Ask the disk controller. CPU doesn't directly ask the disk controller. Actually, it uses some software, which is the device driver. The operating system asks the device driver to transfer some data, and the process blocks. When the data is ready, an interrupt is generated, then the data can be transferred to the memory. Okay, this is how we see this interrupt